It's a question to you, actually. Are we more comfortable with the universe that began, or would we be more comfortable with the universe that had always existed? But that almost makes the universe look, in some ways, like a giant quantum computer, which is not to say that we live in a simulation, right before you ask.
There's so much larger scale that absolutely created everything. Not only did it absolutely create everything, we know the process. We know how it happened. We know how stars are formed. We know how planets exist. We know how gravity is affecting the planets around them. We know so much about all the things that absolutely came out of the universe itself. Why not assume the universe is God?
I mean, it is in some technical sense.
It has to be. It's everything. The universe is everything, including God. If God is a real thing.
If you define God as the creator,
yes,
then you're right. From some point that we don't understand, by the way, the Big Bang. We don't even understand whether that was the origin of the universe, by the way. We understand that something interesting happened.
What is Sir Roger Penrose's? He has
an infinite cyclical universe.
Yes.
And he's trying to answer questions about the very special state of the early universe and why it was the way that it was.
So his model is an infinite contraction and expansion?
It doesn't really contract. It kind of, and I don't fully understand it, and I have asked him about it. But it doesn't recontract. It's not one of those models where the universe expands and then recontracts and bounces like that. It's not one of those. It's somehow, he argues, that when you get to what we usually call the heat death of the universe, where even the black holes have evaporated away, you have conditions that begin to look perhaps like an origin of the universe again. And I can't really fully explain it because I don't really understand what he's trying to say, right? And
wow. So it's not a contraction, it's an infinite expansion then some sort of a metamorphosis?
Yeah, it kind of looks like conformal means there are no sort of distances or time measurements or anything in the universe. It kind of loses all sense of scale, and then you could reimagine that as looking somewhat like the beginning. It's something like that he has in mind, but I really couldn't explain to you. I don't understand what he's proposing.
Wow.
There. So what it does tell you is that we don't know why or how the universe got into the state that we call the Big Bang. So we don't know whether the universe existed before that. We have theories that it did, theories called inflation, which are very popular theories. You'll find them in all the textbooks, which say that before the universe was hot and dense, which we used to call the Big Bang, space and time is still there, and the universe is expanding extremely fast. It's called inflation. And then that period draws to a close. And that expansion sort of slows down and almost collapses and changes. And the energy that was driving the expansion gets sort of dumped into space and changes and ultimately makes the particles out of which we are made. So that's actually the standard model of cosmology now. So we do have an idea that we redefine the Big Bang as the hot Big Bang, and it's not the origin of the universe in time. It's the end of inflation. And then you get the question, what is inflation? Did that have a beginning? And the answer is that in Einstein's theory alone, then yes. And Roger Penrose actually and Stephen Hawking proved this a long time ago, that just given Einstein's theory, you have this singularity, kind of like the black hole singularity, but at the beginning of time. But we do know that when you put quantum mechanics in and add that in, then it gets messy and we don't really know what that means. And so Stephen Hawking had a thing called the no boundary proposal. There's all sorts. Basically, the point is we don't know. So we don't know whether the universe had a beginning in time, I would say is the correct statement as we are at the moment. It's part of the reason why, by the way, getting back to the black holes, they're important and interesting because the study of black holes and this idea of information and how does it get out, that's leading us to suspect that space and time themselves are not fundamental, but they emerge from something else. So just in the way that we've been talking about consciousness emerging from this physical structure in our heads. So we don't know how it emerges. It's a very strange thing, but it emerges from this collection of atoms, right, in a particular pattern. Well, we think now, from the study of black holes, that space and time emerge from something else, which is kind of, one way to describe it is just a quantum theory. So it's in quantum computing terms, it would be just qubits. So a network of qubits entangled together, just like a quantum computer. out of that, we suspect that space and time might emerge. So surely we have to understand that process, and we don't really fully understand that, but we have glimpses of it in much more detail to start talking about the origin of time. Because in order to talk about the origin of time, you have to know what it is. And we don't actually know what it is, which is, and that's kind of, when you say that, it sounds bizarre, doesn't it? Well, how can you not know what time is? So, but it's funny, it's interesting that the study of black holes is forcing us towards these theories. It's not that we had the theory, space and time emerging from something, and decided we could check it by thinking about black holes. It's come the other way round, really. So it's interesting. But that almost makes the universe look, in some ways, like a giant quantum computer, which is not to say that we live in a simulation, before you ask, but it just looks like there's a description of the universe that looks like a quantum computer type description. Now, that doesn't have the concept of space or time in it.
Is it possible that is what it is, and that the universe was created, and that as we're talking about, super intelligent life forms keep constructing better versions of itself and better versions of computers to the point where it can construct the universe itself? If we're seeing the code, if we're seeing the evidence, we're seeing something that mimics a quantum computer. We're like, couldn't be that.
It is. It's interesting that you're right, and that's a good way of phrasing it. Mimics or looks like a network of qubits. So it looks like some kind of quantum computing description is available to us for the universe. But I don't think you can infer much from that. It just passes the question further back. As I said, we have never understood what it means for the universe to have a beginning. We don't really know that. And so this is the same. I think it's just the same question. It's like, well, you ask, if it really is a network of qubits, it could have been there forever, that network of qubits. Actually, in quantum theory, it's more natural for it to be just eternal. And it's an interesting question. I once gave a talk, actually, a conference of bishops. They were Catholic bishops. And they asked me to go and give a talk at their conference about cosmology. And so I gave the talk about cosmology, and they all listened. And we had a question thing afterwards. And I said to them, what happens if we discover the universe has always existed? Because it might have. We know there's a thing called the Big Bang, but it might have been something that happened in a pre-existing universe. Maybe that's eternal. What does that mean for your sort of picture of a creator? And I don't know. I was asking it's a genuine question.
Right.
They thought it was a cool question and didn't have an answer, right? It's a question to you, actually. Are we more comfortable with a universe that began, or would we be more comfortable with a universe that had always existed?
Comfortable is a weird word, because I always wonder if our whole desire to form the universe in terms of a beginning and an end is based on our own biological limitations. The fact that we have a birth and a death, we try to apply that to the universe itself, because we know that stars didn't exist, and they do. They burn out. We know planets lose their atmosphere. We know things change and all these things. So I think we think, this sun's going to die out. The universe probably had a beginning too. But why? There's no reason to think it did. It's much more likely that it's always existed than it didn't exist, and then it became out of what?
Yeah.
If the universe didn't exist, so there's nothing in the whole of observable everything. There's nothing. Yeah. And then all of a sudden there's something. That seems less likely. It seems more likely that this whole idea of a birth and a death, we have this way of looking at things because of our own limitations. We think that everything has to have a beginning and an end.
And you're right. You've had Sean Carroll on the show, because he always points out that this question, why is there something rather than nothing, presupposes that nothing is more likely than something.
Right.
So whereas it might be the other way around.
Right.
We don't even know that.
Right.
So
but how does something come out of nothing? That's the big one.
The history, I think historically, I think it's right to say that Einstein really felt, I think, that initially that an eternal universe was more natural. But it is also true to say that his theory, general relativity, really doesn't quite rule that out, but it's strongly suggestive of there being a beginning and or an end. So the theory itself, historically speaking, strongly suggests that. And so he changed his mind. And then we saw the universe was expanding, we observed that. And then we've now seen the oldest light in the universe, the cosmic microwave background radiation, which is the afterglow of the Big Bang. So we know that the universe was hot and dense 13.8 billion years ago. We have so much evidence for that, not least that we have a photograph of it 380,000 years after the Big Bang. It's called the cosmic microwave background.
Let's see that. Let me see
We
that
have
photo.
images of that. That's from the satellite called Planck, a European satellite, and also a satellite called COBE. So we have these images of the afterglow of the Big Bang. We also have theories that tell us about the abundance of chemical elements in the universe, which match this perfectly. So there's multiple lines of evidence that tell us the universe was hot and dense. But none of that tells us that that was the beginning. That I think that would be widely accepted. That it's a beginning in Einstein's theory. If you just take general relativity, there's a singularity there at the beginning of time. We don't know what it is, but it's there. But it absolutely is true to say that we think that's not complete as a picture. So there it is. So that is light that was emitted about 380,000 years after the Big Bang. So and the key thing, there's so many things to say about these images, but one thing is that those colours correspond to regions of very slightly different density that we've detected now in the gases of the young universe. So that greeny one, that's from the Planck satellite. So those colours correspond to regions of different density. So in this young universe, 380,000 years after the Big Bang, that's only hydrogen and helium gas. So you've got an almost smooth, almost featureless universe then. But these little density fluctuations are very important because as the universe expanded and cooled, they collapsed to form the galaxies. So without those ripples, without that pattern, we would not exist. Nothing of interest would exist. And so the question is, where did that come from, that pattern? It's fundamentally important. And the theory of inflation that I mentioned earlier, that there's this time before the universe got hot and dense, that theory predicted that pattern before it was observed. So this idea that you've got this very quickly stretching space. And by the way, the stretch, if I can remember the number, is if you consider 2 points in space during inflation, the distance between them was doubling every 10 to the minus 37 seconds, which is 0.00000, 37 noughts, one of a second. So it's incredible rate of expansion that draws to a close. So those theories predicted slight variations in the rate at which inflation stops.
Does the inflation theory, does this work with Sir Roger Penrose's concept? I mean, is it possible that inflation is the far period of the expansion of the universe?
I mean, it is. He doesn't like inflation as a theory.
He doesn't?
But it's right that so our universe is accelerating in its expansion at the moment, which is one of the great mysteries that was discovered in the 1990s by a friend of mine, actually. Brian Schmidt got the Nobel Prize for this discovery. He told me once he'd made this measurement, and it wasn't really, he was looking at supernova explosions, and he'd seen that the suggestion in the data was that the universe is accelerating in its expansion, not slowing down, but speeding up in its rate of expansion. And no one was expecting it, so he thought it was just wrong. But he couldn't find anything wrong with his data. So he published it, and there was no mistake, and he won the Nobel Prize.
Wow.
For that discovery. That's the 1990s. So this idea the universe is accelerating in its expansion, the way that it does that is really important. Is it going to carry on doing that? Is whatever's driving that expansion going to change in some way, which could actually recollapse the universe again? We give it a name, by the way, dark energy, this thing. Mm-hmm. But we don't know what it is. I think it's very fair to say. But it looks a bit like inflation, but it's way slower. So maybe they're linked, maybe it's the same kind of thing. We don't really know. And so it's one of the great mysteries. So, but the universe, it looks like the universe is going to continue to expand forever and to continue to accelerate.
Ask most people what happened at the Big Bang, and you'll get some version of the same answer. Nothing existed. Then, in a single instant, everything did. Time itself supposedly clicked on like a switch.
Essentially what happened before the Big Bang, right? You have to be careful with the language. So if you define the Big Bang really carefully as the time when the universe was very hot and very dense, and as I said, you can't argue with that because we can see it, because we can look out into the sky. Our best theory of how the universe got into that state is that there was a time before that, and it's called inflation.
It's a clean story, and it's the one taught in classrooms around the world. It's also, according to physicist Brian Cox and most of his colleagues working at the edge of cosmology today, almost certainly wrong. The Big Bang, Cox has argued repeatedly, was not the beginning of everything. It may not even have been the beginning of time. And once you start pulling on that thread, an even stranger question opens up underneath it. What if time was never the fixed, ticking backdrop we assume it to be at all? To understand why physicists have moved away from the Big Bang as absolute beginning story, you have to go back to where the story started. In 1915, Albert Einstein published General Relativity, and buried inside it was a bomb nobody had noticed yet. Run Einstein's equations for the universe as a whole, and you don't get a stable, static cosmos. You get one that has to be doing something, expanding or contracting, because gravity never just sits still. Einstein didn't like that answer, so he bolted on a fudge factor, a cosmological constant, purely to force the math back into a steady state.
But the Big Bang was not the beginning. I think Hubble had already seen the expansion, but it hadn't quite got through to Einstein how convincing these results were. So he wanted the universe was just static and stayed there forever.
Right, right.
And then he needed the cosmological constant to do that. That's correct, he would need that. However, he was wrong. When he got convinced, oh no, the universe is expanding, sorry, he said, oh, well, that was a mistake, my biggest blunder, he said.
He would later call it his biggest blunder. But the universe, it turned out, didn't care what Einstein preferred. Within a decade, Edwin Hubble had measured galaxies rushing away from us in every direction. And the further away they were, the faster they were receding. The obvious implication, worked out earlier by Alexander Friedmann and Georges Lemaitre using Einstein's own equations, was that the universe is expanding, and if you run that expansion backward, rewinding the cosmos like a film reel, everything gets closer together, hotter, denser, until you hit a point where the math simply breaks. Physicists call that point a singularity, and for decades, that singularity was treated as the actual starting line of space, time, and everything in it. A day without yesterday, as Lemaitre himself put it. Stephen Hawking and Roger Penrose went one step further in the 1960s, proving mathematically that under general relativity, this singularity wasn't just a convenient assumption, it was close to unavoidable. Time itself, they showed, had to originate at that point. This is the version most of us grew up with. Rewind hard enough, and you smash into a wall. And the wall is where the clock started. Here's the problem. Brian Cox, along with the majority of cosmologists working today, will tell you that singularity isn't a real physical thing. It's a sign that the theory has been pushed past where it actually applies. General relativity is brilliant at describing gravity and the large-scale structure of the cosmos, but it breaks down completely at extremely small scales, the scales where quantum mechanics takes over. And a singularity is, by definition, infinitely small. So when Einstein's equations spit out infinite density and infinite curvature at the Big Bang, most physicists don't read that as here is where time began. They read it as this is where our current theory runs out of road. Hawking and Penrose's own singularity proof rested on 4 specific assumptions, and virtually every one of them, including the assumption that general relativity holds at all scales, is now considered doubtful. So if the singularity isn't the true beginning, what replaces it? This is where inflation comes in, an idea developed by physicist Alan Guth in 1980, and it's central to why Cox and others insist the Big Bang wasn't the ultimate starting point. Guth was looking for a way to solve several nagging puzzles in cosmology. Why the universe is so close to perfectly flat, why the temperature of the cosmic microwave background, the ancient afterglow of the early universe, is almost exactly identical, no matter which direction you look, and why we've never detected the exotic particles that a hot, dense beginning should have produced in huge numbers. Guth realized that if empty space itself carried a tiny amount of energy, tied to quantum fields that exist even in a total vacuum, that energy could drive an unimaginably fast period of expansion before the hot, dense state we call the Big Bang ever got going. Under this model, the sequence isn't nothing, then everything. It's closer to this. A field of energy embedded in empty space inflates a region smaller than an atom into something larger than our entire observable universe, in a fraction of a second. Then that inflationary energy decays, converting into the matter, light, and heat of the hot Big Bang that Gamow, Hawking, Penzias, Wilson, and everyone else since has actually measured and confirmed. Crucially, inflation doesn't require a singularity to kick things off, and it doesn't require time to have a hard starting point either. The Big Bang, under this view, is really the end of one process, inflation, and the beginning of another, the hot expanding universe we can observe. It answers what banged. It says almost nothing about what came before the bang, or whether before is even a question that makes sense to ask. And it gets stranger, because inflation, once it starts, doesn't necessarily stop everywhere at once. In most versions of the theory, it stops in patches, pockets where the inflationary field decays into a Big Bang, our Big Bang, our observable universe, while inflation just keeps going in the space around it, spinning off other patches, other Big Bangs, potentially without end. That's the multiverse, and it isn't science fiction dressed up in equations. It's a direct mathematical consequence of the same inflation model that fixed the flatness and horizon problems in the first place. Alan Guth himself has pointed out that the Big Bang theory, properly understood, was never really a theory of the bang at all. It doesn't explain what banged, why it banged, or what preceded it. It's a description of what happened immediately after some initial event, not an account of ultimate origins. This is roughly the territory Brian Cox has spent years walking audiences through, and where he's been especially blunt is in pushing back on the popular idea that physicists have this fully solved, that the singularity is a settled fact, and school textbooks have it right. When a group of researchers surveyed leading physicists working at the cutting edge of black hole physics and cosmology, asking them directly whether they believed the Big Bang marked the actual beginning of time, most said no. Not, "we don't know." Not, "maybe." The majority position among the people doing this research for a living is that the Big Bang tells us almost nothing about whether time itself had a starting point. Cox has echoed this same conclusion across multiple talks and interviews. The popular picture of the universe blinking into existence from absolute nothing is a simplification that made for a good textbook diagram, not an accurate summary of where the science currently stands. It's entirely possible, under models like Roger Penrose's conformal cyclic cosmology, that our Big Bang was simply the latest in an unbroken chain, the tail end of some unimaginably distant previous universe that expanded, cooled, and thinned out into near-nothingness, only for that near-nothingness to mathematically resemble the hot, dense state of a new Big Bang all over again. Under Penrose's version, the universe doesn't have one beginning. It has an endless sequence of them, aeon folding into aeon, each one unaware of the last. The mechanism Penrose proposes for this is genuinely elegant. If you wait long enough into the far future, every star burns out. Every black hole eventually evaporates away into a thin mist of photons, and the universe becomes an almost empty, featureless expanse. Strip away all the massive particles, and what's left behaves mathematically in a way that's eerily similar to the hot, dense, infinitely small state we associate with a Big Bang, an emptied-out, infinitely large universe and an infinitely small, infinitely dense one turn out to look the same once you rescale the geometry. And that rescaling is the seam Penrose stitches one aeon to the next along. It's speculative, and Cox is careful to say most cosmologists remain unconvinced the evidence supports it over standard inflation. But it's exactly the kind of serious, mathematically grounded proposal that makes the Big Bang was the beginning of everything look like an oversimplification rather than settled fact. None of this is settled science, and Cox is careful about that distinction. The hot, dense early universe, the part we can actually observe evidence for in the cosmic microwave background, is not up for debate. That happened. What's genuinely uncertain is everything upstream of it. What caused that hot, dense state, whether inflation is correct or something else entirely, whether there was a before in any meaningful sense at all. Cox's basic pitch to audiences isn't, "Here's the answer." It's, "The answer you were taught in school was oversimplified to the point of being misleading. And the real frontier is far weirder and far more open than most people realize." Which brings us to the second half of the puzzle, and the part Cox arguably finds even more disorienting to explain. Time itself isn't the fixed, universal backdrop we intuitively assume it is. This isn't speculative physics. It's been experimentally confirmed for over a century, and it follows directly from the same relativity that broke Newton's old static universe in the first place. Here's the intuition almost everyone starts with. There's a clock ticking somewhere out in the universe, a cosmic master clock, and every moment now is the same moment everywhere, for everyone, all at once. Newton believed something close to this. Einstein proved it's false. According to Cox, the second's hand sweeping around your watch face isn't measuring some universal, ticking river of time flowing past you. It's measuring the distance your watch has traveled through space-time, the combined fabric of space and time Einstein's equations describe as a single, unified thing. Your watch, in that sense, isn't really a timekeeper at all. It's closer to a map, quietly recording your personal path through past, present, and future. And because space-time is a single fabric, movement through space and movement through time trade off against each other, speed up through space, and your rate of movement through time slows down. That's not a metaphor. It's measurable, and it's been measured directly. The classic illustration is the twin paradox. Put one twin on a spaceship traveling close to the speed of light, leave the other one on Earth, and when the traveling twin returns, they'll have aged less than the twin who stayed home. Not because anything mechanically strange happened to their body, but because they genuinely experienced less time, because they moved through space-time along a different path. Slower relative motion through space means faster motion through time. Faster motion through space means slower motion through time. Push a clock close enough to light speed, and from the outside, time on that clock appears to crawl to a near standstill. This isn't confined to thought experiments involving spaceships either. GPS satellites orbiting Earth experience time at a very slightly different rate than clocks on the ground, both because of their speed and because of the weaker gravity they experience at altitude. And engineers have to correct for that difference constantly, or the entire GPS system would drift out of accuracy within minutes. Cox has pointed to this exact example repeatedly, precisely because it's not exotic in the slightest. It's sitting in the phone in your pocket right now, quietly correcting for the fact that time genuinely runs at a different rate, a few hundred miles above your head, than it does at sea level. Physicists have also flown atomic clocks on commercial airliners, compared them against identical clocks that stayed on the ground, and measured the tiny predicted difference directly, down to a fraction of a billionth of a second. It's not a hypothesis anymore. It's an engineering constraint. Gravity complicates the picture even further. And this is where Cox likes to reach for one of his favorite examples: black holes. Time doesn't just slow down the faster you move, it also slows down the deeper you sit inside a gravitational well. Drop a clock toward the event horizon of a black hole, and viewed from a safe distance, that clock appears to run slower and slower. Its ticking stretching out until, right at the horizon itself, it appears to freeze entirely, forever, from your outside vantage point. But that's only how it looks from the outside. If you were the unfortunate person actually falling in along with that clock, your watch would seem to tick along completely normally to you, right up until the much more immediate problem of the black hole itself. Cox uses that split perspective deliberately because it captures something crucial about relativity. There is no single, agreed-upon now shared by every observer in the universe. Two people moving differently, or sitting in different strengths of gravity, will genuinely disagree about how much time has passed, and both of them are correct from their own frame of reference. Time isn't fixed. It's relative to the observer, woven into the same fabric as space itself, and that fabric can stretch, bend, and warp depending on speed and gravity. This is where the third piece falls into place: what space and time actually are, once you strip away the everyday assumptions. Newton pictured space as an empty, unchanging stage, and time as a separate, universal clock, ticking the same for everyone, everywhere, totally independent of what was happening on that stage. Einstein tore that apart and replaced it with something stranger and, in a real sense, more unified. Space and time aren't two separate things running in parallel. They're a single four-dimensional structure, space-time, and what we experience as gravity isn't a mysterious pulling force reaching out across empty space, the way Newton imagined it. It's geometry. Massive objects like stars and planets bend the fabric of space-time around them, and everything nearby, including light itself, simply follows the curves in that bent fabric. The Earth isn't being yanked toward the Sun by some invisible cord. It's rolling along a curved path in space-time that the Sun's mass has warped, the same basic way a marble rolls toward the dip made by a bowling ball sitting on a stretched sheet. That's a strange enough idea on its own, and Cox has spent whole television segments trying to make it visually intuitive, stretching a rubber sheet taut and rolling a bowling ball across it to show how a smaller marble curves around it, not because anything is pulling the marble, but because the marble is simply following the straightest possible path through a surface that's no longer flat. Einstein arrived at the same insight through a thought experiment rather than a rubber sheet. Imagine you're standing in a sealed box with no windows. If the box is sitting on the surface of a planet, you'll feel your weight pressing your feet to the floor. If the box is instead out in deep space, accelerating upward at exactly the right rate, you'll feel the exact same sensation, indistinguishable from gravity, with no way to tell the two situations apart from the inside. Einstein called this the equivalence principle, and it's the seed that grew into general relativity. Acceleration and gravity aren't just similar, they're the same underlying phenomenon. Both of them expressions of curved space-time rather than separate forces acting on separate stages. But Cox pushes it one step further, into territory that unsettles a lot of people the first time they encounter it: the block universe. If space-time really is one unified four-dimensional structure, then the past, present, and future aren't fundamentally different categories of thing. They're all just different locations within that same structure. Under this view, your birth, this exact moment, and your eventual death are all, in some sense, equally real points sitting within the four-dimensional block of space-time. Nothing is flowing past a fixed present moment the way it intuitively feels like it is. The sensation of time passing, of the present moment being special or singled out, Maybe something closer to a trick of human perception and memory, rather than a fundamental feature of the universe itself. Cox doesn't claim this settles the philosophical debate over what time really is, and plenty of physicists still argue over exactly how seriously to take the block universe picture. But he's consistently pointed out that nothing in relativity actually requires a universally flowing present moment, and a great deal of the mathematics works more cleanly if you drop that assumption entirely. Put all three pieces together, and you get a picture of the universe that looks nothing like the one most of us picked up in school. The Big Bang almost certainly wasn't a singular instant when time itself switched on from true nothingness. It looks far more like the tail end of an earlier process, inflation, a prior cosmic cycle, or something we haven't even correctly identified yet, that we simply can't see past with our current tools and theories. Time isn't a universal metronome ticking the same beat for everyone in the cosmos. It's a personal, bendable dimension, stretched and compressed by speed and gravity, differing from observer to observer in ways that have been tested and confirmed again and again. And space and time together aren't a stage and a clock. They're one interwoven fabric, within which gravity is just geometry, and the flow of time may be less fundamental than it feels from the inside. None of this makes the universe less coherent, and Cox is emphatic on that point. It makes it stranger, yes, but also considerably more interesting than the tidy version most of us were handed as kids. The honest state of modern cosmology isn't a finished textbook chapter with a clean answer at the back. It's an active, ongoing argument at the edge of what current physics can actually test. And the people working closest to that edge, Cox very much included, are the first to admit that the beginning of everything and the true nature of time itself remain genuinely, deliberately open questions.